think about that for a few minutes. While you're doing that, I'll talk a little bit about next week's exam. We're just 1 week away now. I believe today is the 10th, and that's on the 17th. Unfortunately, it's scheduled for very late in the afternoon. I believe the start time is listed as 5 o'clock. Just was the only thing we could do with it at that particular time. So that'll be kind of a late starter and late ender. Although the exam will not take you long. It's 50 multiple choice questions. I just guarantee you that for the most part, the questions are intended to be, and hopefully will turn out to be, very straightforward. I'm not going to say simple because that might be misleading, but straightforward is the approach that we like to take. You may look at some of the questions and go, is this question really as simple as it appears? And the answer is yes. Don't overread the questions. They're meant to be short questions, short answers, and pretty much mainstream for any of the topics that we've covered. I'll give you an exact cutoff for when we'll stop using materials for that exam. It might be after today, or possibly if we're still doing a little bit of the intro to autonomics on Tuesday into that. But I'll be very, very distinct about letting you know where the cutoff is. It will not go beyond this introduction to autonomics, however. Whenever we finish that up today or Tuesday, that will be the cutoff, and we won't, even though in class we'll have started the specific aspects of parasympathetic pharmacology by then, that will not be included on the first exam. That will be the first topic for exam number 2 a few weeks down the line. So study hard. I don't mean to imply don't study for it because it's straightforward. I want you to study real hard, get everything out of the material, current material that we possibly can. But it's very, very general stuff on this first exam. The later exams will be very different in that once you get into the specific drug groups, of course, then you have a lot of names to deal with and specific actions associated with those substances in that particular category. And so that's kind of a different deal. But this first exam is really pretty much completely review generalized types of material. So anyway, we're coming up on it, and have more to say about it each day next week. In the meantime, I'm sure you have plenty of other things to do. If you can get a head start on studying for this exam, it would be tremendous. But I don't know whether your schedules allow for much of doing things ahead of time or not. So anyway, there's some thoughts on my part with respect to the first exam. As I think I've tried to say along the way, and particularly probably in the first lecture, students tend to do well in this course and in the companion course coming up in the spring. So, if you can be heartened by the idea that historically people have done well on the exams and done well with the grading in the course, maybe that can relieve a little bit of tension on your parts. So whether it's today or upcoming days, I'll certainly welcome any questions that you might have while we're having class, or if not, by email or some other way of connection is certainly fine also. Okay, well, as we started off on the lectures yesterday, I brought in an article from Chemical and Engineering News about these highly reactive fluorinated hydrocarbons known as PFAS. And we sort of went through some preliminaries in that particular regard. And just to remind you that the reason for covering this at this point is the incredible importance of this topic. As the article estimated, there's somewhere in the range of 5,000 of these fluorinated hydrocarbons have been synthesized. We know very little about most of them. Some of the more prominent ones, we've learned enough about them to know to be cautious. They're pretty dangerous substances and are widely distributed in water supplies throughout the world. So what got this particular article going was some people in New Hampshire who became alarmed about the presence of these substances in their water supplies. And they had never heard of these substances before that discovery. And as I said the other day, I had never heard of these substances either until very recently, yet they're there, and there's considerable preliminary toxicological evidence to suggest that they should be regulated and that we should be very cautious about exposing ourselves, our families, etc., to these substances. So let's take a look at some other aspects of this important topic. Here as we do this current event thing today, and then you can be sure that when we get to our toxicological segment later in the course, this issue as well as other issues associated with drinking water will arise. So the next segment of this article is entitled Ramifications of Limits, and it starts in the following manner. If the EPA limits PFOA and PFOS in drinking water, regardless of how it happens, some utilities, especially small ones in rural areas, are worried about the cost of filtering the chemicals out of tap water. Then there's the question of what to do with used filtration media or highly concentrated waste from systems to ensure that captured PFAS don't get reintroduced into the environment. At present, there are no commercially available technologies that break down PFAS in water, though promising ones are in development. And sort of buried within that is, I'll just sort of comment on that a little bit, is the idea that, once you start off with an area of pollution, let's say by identifying substances and synthesizing new compounds in that category, you've got them. I mean, even in terms of things which are much more labile than these substances, you've got all the synthetic apparatus, all the storage apparatus, all the hardware and so on associated with it that's contaminated with these substances. Landfills get contaminated by these substances, water supplies, etc. It's just pretty ubiquitous once you start down this pathway. And really, what it is when you get down to it is it's a ramification of the second law of thermodynamics. It's an entropic sort of situation. The disorder values become very, very high, and it's tremendously costly in terms of both dollars and energy to rectify that disorder that's been created by those processes. So going on with their writing, it says drinking water providers aren't the only public utilities concerned about what the EPA might do. PFAS, and this is kind of what we were talking about a minute ago, enter wastewater from consumer goods, from runoff, from landfill, leachate, and industrial sources. Sewage treatment facilities have told the EPA they are anxious that a drinking water limit tighter than the advisory level of 70 parts per million, which we talked about the other day, could lay the regulatory groundwork for a limit under a different statute, the Clean Water Act. And that's a little bit confusing. There's the Clean Water Act is one of the areas of regulation. And then there's another piece of legislation known as the Safe Drinking Water Act. Those are different pieces of legislation, and the specifics of that particular legislation differ between those two things. Using the Clean Water Act could require sewage treatment facilities to filter out these compounds before they discharge treated wastewater into rivers or lakes. There's a number of things here in the writing then that sort of continue along this lines of how complicated it is to deal with this stuff. And then that leads to the final paragraphs of this article, which I'll get to now so that we don't take any more time with it. The New Hampshire activists maintain that to protect public health, the nation needs a single drinking water limit for all of these compounds and related substances. So in other words, rather than two regulatory acts, one congruent regulatory act that cuts down on sort of the confusion that exists in a governmental regulatory sense. To regulate these compounds out of an entire class of thousands is really missing the mark, say the New Hampshire people. The reality is most people aren't exposed to just PFOA or PFOS. We are exposed to a mixture of these chemicals, recalling that tests of the family member's blood detected multiple PFAS in these individuals. And that gets to that idea of environmental burden that I talked about the other day, where we're thinking about a very complex mixture of substances, some at very low amounts, some at higher amounts. What are the implications of the exposure to the mixture of these substances? And the answer to that is we don't know. And what these people in New Hampshire are trying to foster is the idea that we need to do more. We need to more highly regulate these substances, and we need to do more research in these areas. So I thought this was an important enough topic for all of our health and our family and colleagues' health and so on to bring it up and raise it to a little level of our consciousness of it. I know it did mine. Hopefully it's elevated your understanding of these topics a little bit too. With that, I'll stop and see if anyone has any thoughts or questions in this particular regard. Kind of a downer of a topic, all right. See if maybe we can brighten things up a little bit as we proceed through the rest of our hour. Okay, so what we're doing currently is reminding ourselves about some key aspects of autonomic biochemistry, physiology, and anatomy that are relevant to our understanding of autonomic pharmacology. Because as I tried to emphasize yesterday, the real name of the game in my mind here is not so much the pharmacology itself, because that falls into place if we have a good grounding in the introductory aspects of autonomics from a neurochemical, anatomical, and related sorts of foundational senses. So let's do some more of this today. We'll be talking about the parasympathetic drugs later on, especially next week when we move past this introductory phase. Once again, remember, if there's anything that's confusing or not working out, or is working out but you want more detail or something like that on it, please feel free to jump in at any point along the way. So there's our sympathetic nervous system cat, Francis, showing us some of the key characteristics of the fight, flight, fright, or freeze syndrome, which is named after really the long ago evolutionary components of this response. But that isn't to say it isn't as viable today as it was thousands or many tens of thousands of years ago during evolution of these systems. people, of course, are under stress in 2020, and that stressful component, initially plays out in terms of the very rapid responses of the sympathetic nervous system. The reorienting of that situation from a homeostatic standpoint comes from the linked parasympathetic system. And so the two systems operate very much in that complementary sense. Let me skip to this slide entitled Some Autonomic Reminders, Anatomical, Neurochemical, and Functional. And I may not be able to totally stick to it in exactly that order for the whole way. Some of these things, of course, impinge upon each other, and the anatomical things, aren't of that much interest to us, other than the implications that they have in a neurochemical and a functional sense. So there'll be some crossing of boundaries here, but I'll do my best to keep it straight as we go along. I find it to be a extremely fascinating subject. So I may go on and on a little bit in some of the cases, and if I'm overdoing it, jump in there and say, get moving here, bud. We've got some other things to talk about. So from an anatomical standpoint, the autonomic nervous system, sometimes called the automatic nervous system, is a peripherally oriented nervous system. That does not imply, however, that the central nervous system, the brain, doesn't have regulatory input into the peripheral system. It certainly does. In areas like the hypothalamus and closely related ancient areas of the brain, such as in the diencephalon, are all very much involved in regulating emotion, regulating deeply seated important functionality, such as you find with the autonomic nervous system. So, any drug substance that penetrates the blood-brain barrier and finds target sites, for example, in the hypothalamus, may ultimately produce ramifications as far as the peripheral output of the system is concerned. So we have to keep that in mind. And as we move more into central nervous system neurochemistry and pharmacology later in the semester, we'll certainly be taking those reminders and looking at the implications of central nervous system function on the periphery. But that said, you can think about the autonomic nervous system very much in the context of peripheral physiology and neurochemistry as the most quote unquote straightforward aspects of autonomic function. So when signals come down the brain, through the brain stem into the spinal cord and eventually exit the central nervous system, they encounter the autonomic nervous system in a two neuron sense. So there's the connection that the first neuron has with the central nervous system, be that connection coming out of the lower brainstem or into the spinal cord. And then that first autonomic neuron synapses with a second autonomic neuron, which in turn synapses at the end organ level. So in other words, that second neuron finds an organ level connection, in places like the heart, the lungs, the GI tract, the pupils, et cetera. There are multiple places that the autonomic system contacts the peripheral end organ areas, which are the things that were really important for us to think about, because we want to know, how is the autonomic nervous system regulating liver function? How is it regulating kidney function? What are its aspects that are critical to homeostasis with respect to the vasculature, the heart? to secretory organs, etc. So all of those components comprise our vision of what's going on with respect to the autonomic system and how that can eventually parlay itself into drug action of one type or another. So before pursuing a little more detail along these lines, let me remind ourselves that there's another central to peripheral connection known as the somatic nervous system. And that's the regulatory aspects for skeletal muscle. That's a very different system from the autonomic nervous system. The autonomic system essentially regulates smooth muscle and secretory things in the periphery, whereas the somatic nervous system regulates, the widespread reaches of skeletal muscle function. Now, one of the places where that can get a little bit confusing, and I won't do too much with that right at the moment, but I'll do a little bit more in a few minutes, is that there's some very similar neurochemistry associated with the somatic system and the autonomic system, which can from a learning standpoint, can confuse us. And so we'll try to keep those things straight as we go along. So I just wanted to mention the somatic system. That's not really, part of our emphasis right now. Later on in the semester, when we're talking about neuromuscular blockade and so on, we'll be talking about the somatic system. But right now, except for comparative purposes, we're pretty much isolating our viewpoint to the autonomic system. So the two neuron level of the autonomic system, is connected between neuron 1 and neuron 2 by what is known as a ganglion. And a ganglion, of course, these systems, I talk about it as if there's one neuron here and one neuron there, but there's, of course, huge numbers of these neurons that are proceeding in common with each other. And as the first neurons of the autonomic system synapse with the second neurons of the system, they do so at what's known as a ganglion. And a ganglion is just a fancy name for a collection of nerve cells. So whether we're talking about parasympathetic system or sympathetic system, the first neurons synapse at the ganglionic level with the second neurons in the system. Now, let me bridge over into the neurochemical just a little bit here to make what I hope is a very important point about the ganglia. As the first neuron synapses with the second neuron, the neurotransmitter that's being released at those sites is acetylcholine. Whether it's the parasympathetic system or the sympathetic system, the release of neurotransmitter is the same in both those systems. And the contact on the postsynaptic side, in other words, the receiving part of the second neuron, is by acetylcholine receptors, or often called cholinergic receptors of the nicotinic type. So if you recall, nicotinic receptors from our review are ion channel receptors. So at this particular level, we're basically talking about neurotransmission, which involves ion channel functionality, whether it's parasympathetic or sympathetic. Now, the key point here is, since the neurotransmitter is the same, the receptors are the same, and the functionality is shared between the ganglia at the level of the parasympathetic and the sympathetic system, you cannot differentiate between the sympathetic and the parasympathetic at the level of the ganglia, because the neurotransmission is identical. So in a sense, although that may seem a little bit bizarre, in a sense, it simplifies our job in the pharmacological realm by saying there's really not a lot of meaningful pharmacology at the ganglionic level, because typically what we're trying to do in the drug realm with respect to autonomic pharmacology is to target one system or the other, to target parasympathetic or to target sympathetic. Because when the system goes out of homeostasis, typically what's going wrong is that balance that exists typically between the parasympathetic and the sympathetic is lost. And for example, you get too much sympathetic tone or too little parasympathetic tone. And what you have to do with drug tools is try to bring those back to a more level area. You can't do that at the ganglia because as you hit one of the systems, you hit the other one too. Um, so it's kind of a tough thing to get a handle on, almost in the sense that it seems counterintuitive, but the pharmacology that we're talking about, will be talking about, as far as autonomics is concerned, is at the level of the second synapse, where the second neuron is impinging upon the blood vessel or the secretory cells or whatever it might be. So we can say pretty short thrift with respect to the ganglionic level of biochemistry, neurochemistry, physiology, and anatomy, because it's really not all that significant as far as pharmacology is concerned. Now, when we get to the ganglionic pharmacology here in just another week or two, we'll see that there are some agonists and antagonists that are available, and we'll learn a little bit about those at the ganglionic level. But the complications of understanding that are pretty minimal because of the commonality between the two systems. So the name of our game will essentially be out farther out into in the periphery as the system is synapsing with the end organs. Now, before leaving the ganglionic level, let me say a couple of other things which have some level of importance as far as autonomic physiology and pharmacology is concerned. And that is the output from the central nervous system to the parasympathetic system is sort of what we call high-low output. The entry levels into the periphery are from the central nervous system at the cranial nerve level, so basically emanating out of the brainstem, so way up as far as the connections to the periphery are concerned, and then the sacral region, way down at your bottom. So sometimes the parasympathetic system is called the cranial sacral system because of that anatomical distinction, high and low. The sympathetic system, on the other hand, emanates from the CNS in the middle regions, the lumbar and thoracic regions of the spinal cord. So sometimes the sympathetic system is called the thoracolumbar system because of that anatomical distinction. Now, that might not mean that much, except for the fact that the output, high and low versus sort of middle ground, is a little bit different anatomically for the two systems. So, for example, the parasympathetic output finds contacts in ganglia, which are pretty much located on or near the end organs. The sympathetic output, on the other hand, emanating from that thoracolumbar region, encounters a communicating channel that's right parallel to the spinal cord. The ganglia are all located at that level rather than out at the end organ levels. So the implications of this physiologically and functionally are that you can get communication in the sympathetic system up and down that chain. It's often called the chain of ganglia, Um, whereas the output is a little bit more discrete with respect to the parasympathetic system because it's not encountering a chain from that first neuron, but rather isolated ganglia out at the end organs. And, you know, it's a little bit dangerous to speculate about what the sort of evolutionary advantage of having this type of distinction is, but I'll just postulate that the reason is for parasympathetic output, just an hour ago, you folks finished up with your midday meal, hopefully. You know, at that time, we need parasympathetic activation. And what we really need is parasympathetic activation at the level of the gut, uh, not necessarily other places. So that more sort of focused parasympathetic output that you can get because of the location of the ganglia is actually an important matter in a physiological sense. Whereas over on the sympathetic side, when danger or stress arises, you need the whole sympathetic system to be activated rapidly and at once. You 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 not only need the heart to go faster, you need the blood vessels to constrict, you need certain glandular secretions, you need relaxation of smooth muscle in the lungs so that you can breathe better. You need pupillary dilation so you can get as much light into the eyes as possible. You need all of that together. And the activation of that chain of ganglia allows that sort of all at once sort of activation, rapid activation of the sympathetic system. So despite it seeming to be kind of a esoteric sort of difference between the parasympathetic and the sympathetic systems at that anatomical level, it really it goes beyond being esoteric to being very, very practical. So some take-home lessons as far as the ganglia are concerned. At the neurochemical level that we talked about a few minutes ago, we really can't distinguish between parasympathetic and sympathetic ganglia. At the so neurochemical, it's all nicotinic cholinergic. At the anatomical level, however, the sympathetic system is a much more concerted all-at-once system than the more discrete ramifications of the parasympathetic system. So initially a little bit hard to keep those things in mind and distinct from each other, especially when, you know, I'm not a good judge really anymore of how well I've described the similarities and the differences. So think about those things a little bit. And if there are questions now or later, for that matter, feel free to ask those, and I'll do everything that I can to clarify what's going on there. Any questions at this juncture? Okay, well, good. I hope that's sort of sounding like review to you. Uh, Now let's venture farther out into the periphery at the level of the second neuron synapsing upon some end organ along the way, be it, let me just back up here a little bit. Whether we're seeing a synaptic connection at the pupillary level and giving dilation like we see with Francis with respect to the sympathetic system, or here where we're seeing activity at the pupillary level again, but parasympathetic dominance with the meiotic constriction that we see in the case of black cat here. So sometimes these little animal pictures, I think, can go beyond the level of being satisfying as far as relaxation is concerned to some functional aspects as far as our studies are concerned. So what about these synapses at the end organ level? What about the parasympathetic synapses that we're seeing in action here? Or the sympathetic synapses that we're seeing in action here? Well, here's where some differentiation occurs, because the second level synapse between the sympathetic system and the end organ is an adrenergic connection. In other words, the neurotransmitter is norepinephrine, or in the English system, noradrenaline. Whereas over here on the parasympathetic side, the second level synapse is cholinergic, once again. Ooh, that can be confusing. It really can be. Because we've already talked about the synapses at the ganglionic level as being cholinergic. Here, the difference is one of neurochemistry. If you recall, the synapses at the ganglionic level were cholinergic nicotinic. Here at the parasympathetic level, they're cholinergic muscarinic. Muscarinic cholinergic receptors are very different receptors from nicotinic cholinergic receptors. Muscarinic cholinergic receptors are G-protein coupled receptors, as opposed to the ion channels that we find with in the nicotinic realm. So very, very distinct types of receptors, both in terms of their microanatomy and in terms of the physiology that's the output of their particular actions. So there are subtypes of muscarinic receptors, as there are subtypes of nicotinic receptors. And it's generally agreed upon right now that there are about 5 different major subcategories of muscarinic receptors. Not all of those are important as far as autonomic function is concerned. As far as the autonomic nervous system is concerned, muscarinic subtypes M1, M2, and M3 are the major players as far as parasympathetic physiology and pharmacology is concerned, with other muscarinic receptors 4 and 5, as well as 1, 2, and 3, being important as far as the brain is concerned. So the brain muscarinic pharmacology is a little bit more complicated than the peripheral parasympathetic pharmacology is. So I think one of the most confusing things over the years that I've encountered with respect to initial understanding of these matters is the fact that we find cholinergic aspects at both the ganglia and at the parasympathetic connections to end organs. However, that as we've just discovered, that cholinergic label differentiates between those two, in that the receptors in those two settings are different. Nicotinic in the ganglia, muscarinic at the end organ, as far as parasympathetic end organs are concerned. Now let's think about the sympathetic side for a minute. The norepinephrine neurotransmitter, which is released at end organs of the sympathetic system, impinging upon adrenergic neurons, leads us to another multiplicity of receptor subtypes. Now, from a historical sense, it's kind of interesting to note that the first level of subtypes with respect to adrenergic receptors were distinguished before we ever had the receptors physically in hand. In other words, if we go back many, many decades, if we go back probably, I'm just trying to think, 75 years, well before we physically were being able to manipulate the receptors, this distinction of adrenergic receptors occurred because of pharmacological differentiation. In other words, drug substances which had the capability of differentiating between the receptors, even though we didn't really know what the receptors were. That first level of distinction for norepinephrine or noradrenergic type receptors is known as alpha and beta. And alpha and beta receptors are both G-protein coupled receptors, but they're different types of G-protein coupled receptors. And it's helped us understand those distinctions a lot in recent decades as we've been able to physically probe the nature of these receptors. Now, to make life more complicated for us, but to make the physiology more fascinating, I suppose, is that, as you, I think, already know, alpha and beta are further subtyped into alpha 1 and alpha 2, and over on the beta side, beta 1, 2, and 3, as far as we know right now. You would like to think that that would be the end of this subtyping, but it's not. And uh, the 1, 2, 1, 2, 3 subtypes are further subdivided after that, which I'm not going to pursue much right now because of the complications of that. And I would much rather have us focus in on the idea that there are differences in these adrenergic receptors known as alpha and beta, and that there are subtypes of those receptors, which are small numbers, 1, 2, and 1, 2, and 3 in the case of beta. Now, the distinctions between these receptor subtypes are not only just sort of anatomical in the sense that they're different G protein coupled receptors, but the fact that the G proteins themselves underlie those distinctions, giving us differentiation at the level of signal transduction. So, you know, it's a bit complicated when we take all of those matters into consideration. So, if these are subjects to you which are new or confusing, go for the simplicity first of all. Go for the distinction between alpha and beta, and then the distinctions between the subtypes of alpha and each other and the subtypes of beta from each other. Now, beta is kind of easier to deal with than alpha, in a sense that, as far as we know, beta 1, 2, and 3 are all coupled to the G protein GS. So they're all stimulatory with respect to cyclic AMP is concerned. So I think it's not too difficult to keep the differences between beta in mind, but maybe a little bit more cumbersome over there on the alpha side. The really critical importance to us as pharmacologists is that this differentiation physiologically and neurochemically also results in differentiation at the drug level for us. And so drugs are known, which are capable to one degree or another in differentiating these various subtypes of adrenergic receptors, classically differentiating between alpha and beta, more recently in differentiating between subtypes of alpha and subtypes of beta. Now that gets to be a bit of a complicated deal for sure, but nevertheless, it's very interesting and also encouraging in the sense that, you know, one of the themes in pharmacology, not one that always plays out completely, but one of the themes that's important is to be able to have very discrete pharmacological effects. So you can achieve that to some degree by differentiating, for example, between beta 1 and beta 2. And when we get a little bit farther into our review session here, we'll say a little bit more about that, but we'll really say a lot more about it when we get into the pharmacology itself, because the pharmacology actually turns out to be a blessing in terms of understanding the differentiation between the receptor subtypes in this adrenergic realm. So I think this is a pretty good place to call it good for the day. I'll toss it out there right now to see if anybody has any questions as we close for the day. And when we're done with that, we'll be done, and we'll continue this review in our 1 o'clock session next Tuesday. In the meantime, I hope everybody has a productive and safe weekend, and do everything possible to kind of keep that stress level at a manageable level. Okay, any questions at this point right now? or thoughts about where you might have questions once you can review the material a little bit. While you're thinking about that, just a second, I'll once again promote the reading in our textbooks, really long and detailed in Goodman and Gilman, a little bit shorter and not so much detail in Katzum. And some of the I think in both cases it's chapter 6, if I'm not mistaken, is the introduction to autonomics chapter. You will find topics like we've been talking about here, anatomical, neurochemical, and functional topics associated with the autonomic nervous system in that chapter. And once again, laying the foundation for what we'll see discretely when we talk about the specific drugs upcoming. So even in that introductory aspects in Katzum and Goodman and Gilman, there's a lot more detail in there than what we're doing right now. But hopefully you can use the lecture topics as a guide to what to pay most attention to as you take a look at that somewhat more detailed reading. Okay, anybody have a question? All right, everybody, best wishes. Thanks for your attention. Take care.
Thank you.
You're
Thank
welcome,
you.
everybody. You're so welcome. And thanks to all of you.